Hey guys, welcome back to my channel. How's it going? In this video, we'll dive deeper into conditional probability and explore some important theorems related to it. We'll also discuss the concept of independent events and how they interact with conditional probability. By the end of this video, you will have a solid understanding of these key concepts and how to apply them in various scenarios. So let's get started with the first theorem, which is just a generalization for the theorem which we discussed in our previous video. If we have three possible events A1, A2, and A3, then the probability of all three events occur is given by the probability A1 intersection AB intersection A3 equals to the probability of the event A1 times the probability of the event A2 given A1 multiplied by the probability of A3 given A2 and A1 happened at the same time. In simpler terms, the probability of A1, A2, and A3 all happened is the probability that A1 occurs multiplied the probability of that A2 occurred given A1, and so on and so on and so on. This can be extended to more than three possible events. The key thing here is that these events are dependent on each other. Now let's take a look at the second theorem. Let's suppose that we have an event A which must result in one of the mutually exclusive events A1, A2 until the AN. So we have the event A which results in one of the possible events A1, A2, A3, and so on until the AN. Then the probability of this event A would be equal to the probability of A1 times the probability of A1 given A1, the probability of A given A1, plus the probability of A2 times the probability of A given A2 until the AN times the probability of A given AN. And we can illustrate this visually just using the Euler's diagram. For example, we have the Euler circle, which represents the set A, and this A must result in occurrence one of the possible events from A1 until the AN. So suppose we have A1, and we have A2, and we have A3, A4 until the AN. They are also mutually exclusive. That said, they do not have intersection areas. But you might already notice that the event AJ, it could be A1, A3, A4 or something, does not result that event A has taken a place. So this is what mathematicians call the implication rule in logic. When A implies the event A1, A2, A3 or AN, that doesn't mean it caused the event A itself, because there is also the area which lies beyond the event A. And that said, even if this event A1 occurred, it doesn't always guarantee that event A occurs as well. So this is why it is so interesting. We essentially calculate the total overall probability of an event A by considering all possible scenarios that lead to this A. So we calculate the probability of A happened given that AN happened as well. If that sounds a bit complicated, don't worry, practice makes perfect, and I promise you, you will master the skills over time. Now that we have established this, let's move on to our next point. This is the definition of independence and dependence. Two events A and B are regarded as independent if the occurrence of one does not affect the probability of the other event. Mathematically, it can be expressed as probability B given A equals the probability of B itself, or equivalently, we can say that probability of A intersection B based on our previous formulas will be equal to the probability of B of A times the probability of B. This can be also extended to the case when we have three or more events. Let's suppose we have the events from A1 until the A2, A3, and until the AN. These events are said to be independent only in case when they are pairwise independent. That means that for any two possible events, AJ intersection AR, they equal to the multiplication of these two probabilities. Probabilities of AJ times probability of AR for any possible J and R, which belongs to the set from 1 until the n, and at the same time they should not be equal. J does not equal to B. So this is it. That's it. Each of these possible events are independent. Now let's consider the practical example. Suppose we have a deck of 52 playing cards. Now let's say we want to find the probability of drawing two aces in a row without replacement. So let's say the event A1 is the ace during the first drawn, and the event A2 to be the event the second card drawn is also an ace. So this is the second ace. These events are dependent on each other, because if we already taken an ace from our deck of playing cards, that means that the number of aces in our deck decreases. So let's say we have the probability of event A1 equals 4 over 52. because we have 52 possible outcomes in our sample space, and we also have only 4 possible outcomes for the event A1. We have only 4 aces in our deck, so which equals 1/13. But given that this event has already taken place, the probability of event A2 will be different. It will be 3/51, because we have left only 51 playing cards in our deck and only 3 aces in our deck as well. So that's supposed to be 1/17. And consequently, we have the probability of P1 happened and P2 happened as well. So we basically drawn 2 aces in a row, which equals to the probability of an event A1 times the probability of the event A2 given A1, which equals 1/13 times 1/17 equals 1/221. So this example illustrates how conditional probability can be used to calculate the likelihood of dependent events. In this type of challenges, it is always important to carefully read the conditions that you are given. Understanding the conditional probability and independent events is crucial for solving probability problems. The theorems we discussed here provide a framework for calculating probabilities in various scenarios. And the concept of probabilities helps us simplify these calculations when events do not influence each other. And thank you for watching this video. As always, I hope you found this video helpful. If you have any questions or suggestions, please feel free to leave them in the comment section below. I'm really glad to hear your opinion, and your opinion really matters to me. You can also connect with me via LinkedIn just to stay updated on future contents or engage into other type of discussions. And as always, thank you for watching this video. I wish you all the best and see you in the next episode. Goodbye.